Hello, welcome to the second talk of the afternoon session. My name is Nalini Joshi. I'm from the University of Sydney in Australia, and it's my pleasure to introduce Thomas Willwacher to speak next in this session. Thomas received his PhD in 2009 from ETH Zurich, Switzerland, where he's now a professor of mathematics. He was awarded the ETH Medal in 2010, the Junior Fellowship of the Harvard Society of Fellows in 2010 to 13, the Andrei Lichtenowitz Prize in Poisson Geometry in 2012, and most notably the European Mathematical Society Prize in 2016 for his results in homotopical algebra, geometry, topology, and mathematical physics. Today he will talk to us about little disks operads and Feynman diagrams. Thank you.
Thank you for the kind introduction, and of course it's a pleasure to be able to present my work here. So my plan is to give you a little bit of an overview of the mathematics I've been interested in recent years. What I have to announce is my talk will be shared between mathematical physics and the topology session. It might be a little bit more on the topological side, effectively. So what are the main motivations? From the side of topology, the main motivation for me currently is mostly understanding three types of classical spaces. These are configuration spaces on manifolds generally, embedding spaces of smooth manifolds, and diffeomorphism groups. From the side of, these are a bit abstract things, so think of embedding spaces as knot spaces mostly. So a space of embeddings of M in N is a space of knottings of M inside N. And if you like, another word, instead of studying diffeomorphism groups, of course, mostly one studies the classifying space, and in good cases also the moduli space of M bundles. Now, from the physical side, what I want to study is the perturbative theory of topological quantum field theories, mostly those of AKZ type. So think of Chern-Simon theory and similar theories. So these produce, in particular, topological invariants of spaces, for example, also of knot spaces, and you want to understand how strong are those invariants? What do they capture about your manifolds, knots, or the object you treat? So let me begin by recalling some topological objects, classical topological objects that I will need later. So the first object is the so-called little n disks operad. So it's a collection of spaces D and K, one for every integer K greater or equal to 0. And D and K is the space of rectilinear embeddings of K little disks in a unit disk. So a point in that space will be some configuration of disks in a unit disk. Rectilinear here means that you can scale and translate those little disks, but you're not allowed to rotate or otherwise deform them. So there's one natural operation you can impose on those spaces, namely if you have two configurations of disks, one here, then what you can do is you can take one of those configurations and shrink it and glue it in place of one of those little disks on the other side. For example, if you do that here, so take that, shrink it, put it in place of number 3 here. You just have to renumber the disk. That is you can do it however you want, it doesn't really matter. And the important point is that now you have a new configuration of disk, you forget the boundary of the old disk, and that gives you an algebraic operation. So these algebraic operations satisfy natural axioms, have natural properties. In particular, when you glue something here, you can do it in either order, you get the same result, of course. And if you do nested gluing, so for example, you first glue this here, and then you glue some other configuration here, you can do that in 2 ways. So this gluing is also associative. And when you have these gluing operations plus these axioms, that's called an operad. So more concretely, an operad is the following data. It's a collection of spaces PR one for every R with an SR action of the symmetric group SR. So here it's just renumbering those disks. Then you have composition maps. In our example, these are just gluing of a disk in another disk, and you have a unit element. In our case, it would be just the identity map, the standard embedding of a disk in a disk. And they have to satisfy appropriate axioms that are all modeled on what they satisfy in our example. And in our case, it's called the little disks operad. And this is very important and long studied in topology. There are a few generalizations that you may consider. So one very simple thing, previously we were considering only rectilinear embeddings, so we're not allowed to rotate our disk, we can just allow them to rotate as well. And then there's a similar gluing operation, just again by composing embedding. So that means that if you have a disk which you have rotated and you want to insert something, then the thing you have to insert, first rotate it and then insert it. So very simple. There's a further generalization. If you have, now previously we were just considering configurations of disks in a disk, but if M is any smooth manifold, say, we can consider configurations of disks in the manifold, so just embeddings of disks in the manifold. And these spaces also have a nice algebraic structure, namely if you have a configuration of disks in a disk, and you have configuration of disks in a manifold. Here I've just drawn one, but you could have more. Then you can shrink your disk and glue it in place of this disk here on your manifold. So again, you just compose embeddings. And that means that the space of configurations of disks in your manifold is an operatic right module over your framed little disks operad. Eventually you just have configurations of disks and you have a bit of algebraic structure which is built on these gluing maps. And next thing I need to introduce is a Goodwillie Weiss calculus. So let me give a very simplistic introduction to it. So the main idea is as follows. So suppose we want to study anything about our manifolds. For example, we want to study embeddings. Then the philosophy is, instead of studying that space directly, but study what it does to configurations of disks in the space. So for example, if you have an embedding from M into N, and we have a configuration of disks in M, then just composing with that embedding that we have, we get a configuration of disks in N. Of course, here it's important that it's an embedding, otherwise the disks in the image could collide, and that we don't want. So we have a map from the embedding space from M to N, in the space of maps from configurations of disks on M to configurations of disks on N. And you can easily check that the map such defined is compatible with our right action of the framed little disk operad. So if we glue disks in a disk, we can do that either here or here, and we get the same result. So we have a map from the embedding space to the mapping space of right modules under this operad from here to here. And to make everything homotopically meaningful, I put this H here. I will mostly ignore, for the purposes of today's talk, I will ignore this H. It just means that we take a derived mapping space which is homotopically well defined. Similarly, you could also assume that M is equal to N, and suppose your embedding is actually a diffeomorphism, so it can be inverted. Then of course it goes to an invertible map on the other side, so you have a map from a diffeomorphism group on M into the automorphisms here. And the idea of the Goodwillie Weiss calculus is that exploit those maps to understand the left-hand side. So that's mostly what you do, right? If you have a complicated space, and map it into something simpler and try to study it in here. If you have a complicated group, let it act on something simpler and try to study the action. Like standard theory. Now, fortunately, by work of many years and a very nice result, Goodwillie Weiss and other people have shown that in many good cases, this not only gives you a good amount of information, but even you get a weak equivalent. So for example, if you have two manifolds with and you have codimension at least 3, so n has dimension at least 3 more than m, then the space of embeddings is actually weakly equivalent to this mapping space over here. So that means that relatively complicated space is not space here, can be expressed through, let's say, relatively cheap algebraic structure, just having these disks and gluing of disks. Has quite a fascinating result, I find. Of course, standard criticism is, well, very nice, but this right-hand side is still hard to compute. And so what is my take on this, or what is my program? You don't. The thing what I do is, or what I say is, you should not just stop here, but you should rationalize. So, in very simplistic terms, so M and N are, let's say, smooth manifolds, and configurations on of disk and M and N can also be made manifolds in some sense. And you can just say take smooth differential forms, or take PL differential forms, whatever you want. And then, of course, this is a func that preserves all the algebraic structure. So you have a map from module map from here to here into the same thing on differential forms. Of course, this is contravariant. It changes the order. So you have here the space of maps between forms on configurations in N to forms configurations in M, compatible with the right coaction of forms on the framed little disks operator. And similarly for the automorphisms here. And the main point is now that I claim that, or first of all, it's easy to see the right-hand side is now completely algebraic. There's no topology anymore. Everything's a vector space underneath. And I claim that the right-hand side can be computed. So while this object of the Goodwillie Weiss calculus is hard to compute, this can be effectively computed in many cases, at least. And of course, nobody tells you that this composition is still equivalence. Of course, it shouldn't be a homotopy equivalence. That's too much to hope, but at least you want that it's a rational equivalence. And the hope is that in many good cases it is. And today, actually, I want to pick out one example where everything works nicely and tell you about this example. So where's the physics? That was the only topology so far. So the physics comes about in that you have this topological field series of AKZ type, and the Feynman diagrams which appear in the perturbative expansions can actually be used to construct models in the sense of algebraic topology for all objects that are involved. So the idea is that you use physics essentially, so you borrow the Feynman diagrams and partially also the Feynman rules to build models for everything, and then within those models, or using those models, you can actually compute the right-hand side. So at the end, what you do, you reduce study of these complicated topological spaces to playing with diagrams, essentially. So, if you want, this is another way of doing physics, but instead of doing topological quantum field theory in the standard way by using some push-pull maps to write down some set of differential forms or some invariants of knots or whatever you want, you do it in a very algebraic, very controlled way. Like this, you get a precise information in how strong your invariants are. So if you want, it's an alternative way of doing physics, of doing topological quantum field theory. So one example I want to present to you today is the computation of the rational homotopy type of space of knots. So that is a very simplest example of the embedding space from M to N, when M is actually Euclidean space Rm, and N is also Euclidean space Rn for some higher n. Of course, embeddings from Rm to Rn are relatively stupid, because you can always contract the Rm. So what we do is we actually fix the embeddings outside of a compact. So we say that outside of some compact, our embedding has to be the standard embedding of Rm and Rn, and then inside that compact here, some knotting can take place. that makes the space interesting. And I want to cheat a little further, so I want to simplify a little bit further for my technical convenience. It doesn't matter much. In fact, what I want to do is I want to consider not this embedding spaces, but homotopy fiber over the space of immersions for technical reasons which I don't discuss. The only thing I want to say is that the space of immersions is well understood by Smale-Hirsch theory, so it's just a M-fold loop space of a Stiefel manifold, so this is easy to understand. And so once you know two out of, or once you know either of those spaces, the other one can be understood using using that you have a fiber sequence involving those three. So our goal for today is, I will just put this bar everywhere essentially, and don't worry about it. So our goal today is we want to understand homotopy groups of those spaces. So essentially what we want to do is we want to solve knot theory, at least in high dimensions. There's also a version of the embedding calculus for those cases. So that is due to work of Weiss, Ducoulombier, Turchin. Namely, these spaces M bar, they're weakly equivalent to m+1-fold loop spaces of mapping spaces of operads from dm to dn if n minus m is at least 3. So here it's a little bit different than before. Before we had mapping space of modules, and we didn't have this loop space here, but if in that case one can slightly simplify it, and one can work with a mapping space of operads. One doesn't have to touch modules. Yeah, of course, if you don't know loop spaces, if our goal is computing homotopy groups, then, well, having an m+1-fold loop space just shifts down all homotopy groups m+1 units. So we can just compute homotopy groups, for example, of this space here, and then subtract m+1 from the index. Of course, as I said in the beginning, so what I cannot offer is I cannot understand the whole homotopy type. What I can understand is a rational homotopy type. So in particular, the goal is, or one goal is, understand rational homotopy groups. Understand homotopy groups, tensor Q over Z. So now for the physics. So how to formulate the answer? The answer is non-trivial. And in order to formulate the answer, we need graph complexes. So these are complexes of Feynman diagrams of Chern-Simons type topological quantum field theories, if you want. So we make a graph complex HGC Mn. So M and N are integers, so these correspond to dimensions of our knot. We have a map from embeddings of Rm in Rn. These are the same M and N over here. And then elements of our space should be linear combinations of isomorphism classes of admissible hairy graphs. So hairy graphs shall just be diagrams, think Feynman diagrams, with at least one external leg. So the non-vacuum Feynman diagrams, if you want. Now where do these numbers m and n enter? Well, they enter in the degrees, first of all. Namely, we associate a homological degree to such graphs just by counting vertices and edges. So formally, vertices have degree -n, hairs have -m, and edges n-1. Then what does admissible mean? Admissible means all vertices should have valence at least 3. And this is an important condition. We shall have not odd symmetries. So what is an odd symmetry? If you're used to working with Feynman diagrams, I don't have to explain. But here, for example, the vertices are formally, suppose n is even. Then the vertices formally are even objects. The edges are odd objects. And suppose m is also even, then the hairs are also even objects. And suppose your graph has a symmetry that interchanges the order of the odd objects in an odd way. Then it has an odd symmetry. So then formally we would set the graph equal to minus itself, and then it's 0. Now the point is that these Feynman diagrams have a lot of algebraic structure, and this is one of the kind of take-home message I want to say, is that one should really study the algebraic structure on Feynman diagrams, and a lot of the content can be extracted just from this algebraic structure without actually knowing the field theory underlying it. So here we have a Dihedral structure or an infinity structure. The differential is given by vertex splitting, so we take a graph, then we sum over all vertices and we split that vertex. So we replace a vertex by two vertices connected by an edge and distribute the incoming edges in all possible ways. If you define those signs correctly, I will not say how to do this, then you can check that D squares to 0. So in particular, the kernel of D contains the image of D, and you can study the graph homology, which is the homology of this complex, so kernel of D over the image of D. It's the interesting object that will play an important role later. So basically, this will be our homotopy groups later. There's also Lie bracket. So if you take a bracket of two graphs, this is just given by taking a hair from here and gluing it in all possible ways to a vertex from the other graph. Then you anti-symmetrize so that it is anti-symmetric as Lie bracket should be. Actually, for m equal to 1, so if you're considering one-dimensional knots, it's actually more complicated. You have an infinity structure. Again, I will not discuss that case. Maybe here's a very stupid, very cheap example. So suppose we want to take the differential of that graph over here. Then you have to sum over all vertices and split those vertices. I will not write down all terms, but I will write down a couple of terms so that you see how it goes conceptually. For example, you could split that vertex over here, replace it by two vertices connected by an edge, and then we reconnect in all possible ways the edges. For example, like those three edges could go here, and another edge could go here, or those two could change place, or there are a couple of more options that I haven't written. Then we split this vertex over here, for example, we can split it like this, or in other ways. So just to illustrate how it goes. So it's a completely combinatorially defined operation that easy to understand at least. So now we have, out of our Feynman diagrams, we have a Lie algebra with a differential. And then the point is, of course, at the end we want to understand the space, so we have to get, out of a Lie algebra, we have to get a space. Now how to cook up a space out of a Lie algebra? And there's a standard procedure which is called the Nerve or Moore-Cartan space. First of all, if you have a DG Lie algebra, you can define the so-called Moore-Cartan set. So these are all elements x of degree -1 in your Lie algebra that satisfy the Moore-Cartan equation, dx plus 1/2 xx equal to 0. Situation where you typically know this is if your Lie algebra is, say, differential forms on a manifold with values in some Lie algebra, then that would be the flatness condition for a connection, or for G connection on your manifold. That is how it originally, historically came up. Anyway, for us it's just this equation, so this is a set associated to any Lie algebra. It's given by some algebraic quadratic equation here. Now, how to build a space? We want a space, not a set. So then what we do is, we consider not G, but we consider G tensor polynomial forms on simplices. So delta bullet means for bullet any non-negative integer means the k simplex, and I consider the polynomial differential forms on this k simplex. This is a DG commutative algebra. When I take tensor product of a Lie algebra with a DG commutative algebra, I still have a DG Lie algebra, and I can take Moore-Cartan spaces. And because this object here has a simplicial structure, what I get is not a set, but a simplicial set, and that I just interpret as a space. So the points of that will be points of my space, and the one simplices will be the one simplices of the space, which I glue to the points, and so on. To get a space from a simplicial set, I would just take the realization. And now the main point is that all properties of this Moore-Cartan space that you're interested in, like homology or homotopy groups, can be read off or translated just into properties of this Lie algebra. So actually you never have to really touch this space over here. All computations you want to do, you will translate into computations of on your Lie algebra and then do it there. For example, let me just state one theorem of Berglund. If you want to, let's say we fix one connected component of our Mercator space, so given by some point that you pick a point for some Mercator element, let's say x, and suppose you want to compute homotopy groups with that base point, then what you can do is you just take homology of the Lie algebra twisted by x. Twisted by x means that you add to the differential the bracket with x. The Mercator equation just tells you that this thing here, d plus bracket with x, is again a differential. So here now you have a complex which you can compute the homology of, and this will give you homotopy groups. Now let me come to our result. So let me just recall what we had. So that was the formula of the Goodwillie Weiss calculus. Embedding space was m+1 for loop space of mapping space of operads from the m to the n. And what we can show is that there is a rationalized version of this mapping space. The mapping space from the m to the n rationalized is weakly equivalent to the Mercator space of this hairy graph complexes. So that means that all questions you want to ask about that space topologically can be translated into just playing with diagrams on the other side. In particular, if we use Berglund's result, then we can compute homotopy groups of that space over here, just in terms of the homology of the graph complex on the other side. Now, I've cheated slightly putting the Q over here. Actually, we should put the Q outside, right? But fortunately, here it's the same. So you can show as a lemma that if you so putting the Q here produces you a space which is rationally equivalent to the mapping space without the Q. So in particular, homotopy groups of this space over here will be really the rational homotopy groups of the space you're actually interested in, the one that appears in the Goodwillie Weiss calculus. Now you can use it and plug it into the Goodwillie Weiss calculus, and then you get a formula for homotopy groups of your knot space in terms of homology of the graph complex. So it's important that this holds only in codimension 3. So unfortunately, it doesn't solve all of classical knot theory. It just solves higher dimensional knot theory, where the codimension is at least 3. Yeah, so this I haven't given you a complete history. There's a bit of history, of course. These diagrams have been used for doing knot theory or for computing invariance in knot theory in the past, so that is not new, but our new result is that really you can compute the whole rational homotopy type of the knot space in these diagrams. So they are complete knot invariants, if you want, in higher codimension. But there's a lot of earlier results that we could build off on. In particular, I think one result is, this formula here in a bit weaker degree range has also been shown by Aron and Turchin before. Let me maybe, let's just do one example maybe. So, as I said, essentially the goal here is you want to reduce complicated topology just to playing with diagrams, so something that's a little bit easier, for me at least. And in particular, you can ask, or one thing that's interesting maybe, is question, what is pi 0 of your knot space? So when do you have really interesting knotting of Rm in Rn? There's a classical result of Häfliger that this happens roughly when you try to knot 4k minus 1 dimensional space in 6k space, roughly when one space is 2/3 of the dimension than the other. So let's just try to recall it or reproduce that result here. So we have these formulas, we can just insert k is now equal to 0, so we have to compute Hm, HGC, Mn. And then you can do elementary degree counting. You know all vertices in your graph have to be at least trivalent, and then you can check just by counting, easy exercise that I don't want to do, that all contributing homology classes in HCCMN have to have loop order 0. So they just have to be, they can just be trees. And trees actually, when M and N have the same parity, then there's actually only one graph, which is this. When they have opposite parity, then they're a bit more, but still you can compute easily the homology, and it's again one-dimensional given by this tripod diagram over here. These are the only classes that can occur. And they give rise to non-trivial pi 0 in those two cases. So one of them, the tripod diagram here, corresponds to Häfliger's knots, and the other one is a bit of an artifact of putting the bar, which I don't discuss. So of course Häfliger doesn't consider M bar, he considers knottings of a sphere in Rn, which is slightly different, and this class is a bit of an artifact if you want. But nevertheless, you have reduced that complicated theorem just to playing with diagrams and counting degrees. Of course, you can go further, because in low loop orders, you can explicitly compute the homology of the graph complex, and this gives you explicit formulas for the low order rational homotopy groups in your knot space. So here you see the bounds. So basically, given that for loop order less or equal to 2, we have explicit formulas for what the homology is. Actually, loop order 3, you can also get it, I claim. But here is just shown for loop order up to 2, and then you get, you explicitly know the homotopy groups in this range. You know a little bit more than just low loop order calculations. You also know large families of probably non-trivial classes in your graph complex, and they give you families of non-trivial homology groups, homotopy groups in your knot space. Now, so what we have done so far, essentially we have started with a complicated topological problem and reduced it to just playing with Feynman diagrams. One thing I have to say is that at large the graph homology is not known. So if you ask me what is the graph homology HGC of HGC 2577 in degree 215, I certainly don't have an explicit formula for that. So the next topic I want to discuss is how to actually get information about these graph complexes and the graph homology. Now, in order to do that, even for our hairy graphs, it's good to simplify slightly and consider a simpler graph complex without hairs. So now we're considering vacuum graphs. First, because it's slightly simpler, and secondly, because I need to, I mean, how it comes out at the end, I need to understand this first before I can go on. And so here we're considering now just the vacuum graph, so graph without external legs. Again, we're considering two linear series of isomorphism classes of graphs. Differential is again vertex splitting as before, so we sum over all vertices and then split the vertex. And again, delta squares to 0, and we can compute the homology. Maybe a little bit more precisely, before we had to pick two numbers, m and n. So m was the degree of the hairs, and n was the degree of the vertices. Now, of course, that we don't have hairs, we can drop one of those numbers. So it depends only on one number, n. And n is minus the degree formally of all the vertices. Admissible means the same as before, so it's really just the same thing, just without legs or without hairs. Now, how to get information? So there are a few items of cheap information that you can read off. First of all, the differential splits vertices, and this cannot possibly change the loop order of a graph, right? Because the Euler characteristic is edges minus vertices, loop orders edges minus vertices plus 1, and you add one edge and you add one vertex, so this doesn't change. So actually our graph complex splits into a direct sum or direct product of subcomplexes, one for each loop order that you can study separately. Then if you look at the dependence of graph complexes on this n or m and n, so basically the dimensions of our knots, that was very weak. So essentially, these numbers controlled only in which degrees our graph lands and what counts as an odd symmetry or not. Particularly if you change m and n by even integers, then you will have the exact same graph complex, just that the individual classes live in different degrees. So more precisely, for the non-hairy case, if you change your n by 2 delta n, then every graph shifts by number of loops times 2 delta n. And in the HGCM case, here's the formula. So people in topology, many people are interested in stabilization, so what happens if n and m go to infinity. So here I typically used to say that the stabilization is relatively non-trivial because of those formulas. So if you let m and n go to infinity, let's say in steps of 2, then what happens is that classes of various loop orders, they move up in your table of homotopy groups at various speeds. So that's a relatively complicated stabilization. If you want to see something non-trivial, you would have to take a sufficiently fast-growing loop space to bring them down at, to where you can have non-trivial data. Then next thing, of course, is you can look at low loop orders and try to explicitly compute your graph homology. For example, in loop order 1, it's very simple because suppose we are in the non-hairy case, then the only loop order 1 graph we can build with vertices of valence 2 has this form here. So it's just a string of vertices that closes up on itself. And then you can check, of course this has some symmetries, it has a dihedral symmetry, you can rotate this string and you can flip it. And you can check that via those symmetries, only every fourth of those graphs survives. And depending on whether n is even or odd, which fourth graphs survive shifts by 2. So the formula is that for n even, the graph is 5 vertices, 9 vertices, and so on survive. And for n odd, those with 3, 7, 11, and so on. And for the remainder of the graph complex, so the higher degree, higher loop order pieces, you can check that you can reduce to graphs which are at least 3 valent. And for those 3 valent pieces here, you can obtain degree bounds. So just by, you see every graph has, every vertex owns 3 half edges if you want, and then you can just cook up a simple degree bound given the degree of edges and vertices. I will not even discuss it. Yeah, this is a degree bound here. So you have a bound on the degree given the number of loops. Also, this non-hairy complex also has a Lie algebra structure, which I want to quickly sketch. If you take the bracket of 2 graphs, I mean, before we were attaching hairs. Of course, now we don't have any hairs, so we can't do that. But as a different bracket, what you can do is you can sum over all vertices in one of those 2 graphs. And then you delete that vertex, remove vertex x from your graph gamma, it leaves a couple of dangling edges, and then you put your other graph in place of that vertex and reconnect the edges in all possible ways. That gives you a Lie bracket, you can check, on your graph complex. So it also has a structure of a DG Lie algebra. Actually, your differential is just a bracket with that simple graph in that structure. Now, there are also a few not so cheap results which I can offer. So what we need to understand is homology of GCN for n even and n odd. As I said, if we change n and by just an even number, then homology doesn't change up to moving the classes around. So here's the even case. For the even case, what I can offer is knowledge of the homology in non-negative degrees. So the most interesting thing is that H0 of GC2 is identified with the so-called Grothendieck-Teich-Müller Lie algebra. So I don't even give you the definition of this Grothendieck-Teich-Müller Lie algebra, but I give you a conjecture of what it is. What is shown or what is known by result of Francis Brown is that a free Lie algebra generated by elements sigma 3, sigma 5, sigma 7, and so on injects into GRT. And there's a conjecture that this injection is actually an isomorphism. And these numbers 3, 5, 7, they correspond to the loop order in our graph complex. So more precisely, if I want to write down the generator sigma 2j plus 1, then it starts with a let's say wheel graph here with 2j plus 2 vertices, so wheel with 2j plus 1 spokes, plus certain let's say correction terms. So in particular it has loop order 2j plus 1. There's an explicit formula which I don't want to discuss by using some integrals. Next thing you can do to get some information is you can write down, you can, I mean, at the end you have to compute the homology of finite dimensional complexes, so you can just put it on the computer and let the computer do the work for you. And here's what you get. So here I've plotted the homology of GC2 in various loop orders. The loop order is shown over here. So for example, here we have loop order 1, and then we have one class in every 4th degree. These were the simple like loop classes, just a string of vertices closing up on itself. Here we have so the red lines are degree bounds. Above and below those red lines are all zeros. So all the interesting data is in here. Then in degree 0 you have this Grothendieck-Teich-Müller Lie algebra, which, assuming the conjecture, is just this free Lie algebra. So here you have your generator sigma 3, sigma 5, sigma 7. Then you have non-trivial bracket, the bracket of sigma 3 with sigma 5, so this is in loop order 8. Then you have sigma 9. Then you have bracket of sigma 3 with sigma 7, and so on. So this is a table. And then the computer finds a couple of other entries which are up here. Of course, ideally you would hope that maybe this is it. So here you have your Grothendieck-Teich-Müller, your free Lie algebra, and then all zeros, but this is unfortunately not true. So the goal is how to understand these other numbers. For the odd case, actually have a very similar picture due to, or by completely different origin. So due to Chern-Simons theory, you know many classes in H3 of GC3. And you also have a conjecture of how this H3 of GC3 looks like. So again, in 1 degree, you have at least a knowledge of what's supposed to be there. And you can again put it on the computer. So here's your degree 3. Here you have many non-trivial classes produced by Chern-Simons theory, which you know. And you have your degree bounds. Here you have your loop classes. And then here there's something you don't know. Fortunately, it's not all zeros. So one question is how to explain those numbers. Of course, ideally, or like the ambitious project is give closed form solution for the dimension of Hj of GCN in loop order k, but that is currently far from solvable. So, for example, even the question whether this line is all zeros was more or less a conjecture independently raised by Drinfeld and Kontsevich, and they both failed to solve it. So it's not completely easy. I mean, of course, they didn't use the language of graph complexes, but yeah. One question is how to get information in other degrees. And here I just want to give you one quick trick. So suppose you have a complex and you want to compute the homology, and it's too complicated, you can't do it. Then like one trick you can do is, if it's too complicated to compute the homology with respect to differential delta, then maybe you can compute it if you change your differential delta by adding some d. Of course, you have to do it in a little bit clever way. You cannot just take d equal to minus delta or something. That would make it very simple, but you have to use it. You have to do it in a little bit clever way by taking this d small in some sense. So you have to have a filtration such that this d is in higher orders. And if you can compute your homology with respect to this altered differential, then from the spectral sequence you can actually obtain information of about your homology. And statement is here you can do it. You can find such deformations such that the altered complex has very small homology, just one-dimensional. That means that in your spectral sequence, all classes, except those ones here, have to kill some other class or be killed by some other class. So all classes come in pairs. And yeah, here's a more precise theorem. I don't want to discuss it. Let me just show you the picture. So here are the pairs that cancel each other in the spectral sequence. So you can check, and it's quite nice, that these simple loop classes in loop order 1 precisely cancel the generators of your Grothendieck-Teich-Müller Lie algebra. That I found quite a beautiful thing, because they are relatively complicated, and these loop classes are totally stupid, totally simple. But still, the simple objects cancel these very complicated objects. Anyway, so you have accounted for all your generators, but of course there are many more objects in your Lie algebra than generators. Namely, all brackets are not accounted for yet. So every bracket needs another partner. So for example, the first bracket was here, or sigma 3 bracket with sigma 5, and that needs a partner, and it's precisely the first higher dimensional class you find over here. And similarly, you can account for all those classes here. Well, okay, this one is a bit too far, there are too many zeros where it could cancel, but basically all the known classes that are found by the computer are accounted for by this mechanism, that you have a free Lie algebra, and every element has to have a partner. In the odd case, you have a similar picture. So if I want to give some summary, and my number is that's still non-negative, but also not positive. Point is that you have a known 1 degree in which you more or less know your graph homology, and you have these spectral sequences which let you create from these known classes a lot of other classes in other degrees, and that at least explains the homology that we see by the computer. Of course, it doesn't explain everything. And actually for the hairy case, you have an identical picture. I don't want to discuss it, but it's identical. Okay, so thanks a lot for listening. That was my talk.
The schedule doesn't allow for too many questions, but if somebody's got a quick question that they'd like to ask now, please raise your hand. Yes.
Is there maybe some quick explanation why these hairy graphs appear? Why exactly this flavor of Feynman diagrams appears?
Yeah, explanation. I'm not sure if I can give a good. I mean, what's your background? Are you a not theorist, or? Of course, my explanation is just that it comes out of the calculation. If you, of course, in knot theory, these diagrams have long been known. Like, for example, if you restrict to the top degree piece where all graphs are trivial, your invariance, you get just a classical finite type invariance of knots. So it's in other degrees, I mean, what I would say is, if you write down the Feynman diagrams of your topological field theory, underlying this, so generalization of Chern-Simons, and then compute their homology, and then they will give you a model for the configuration space of points in Rn. That is actually the underlying connection point where you make contact between the diagrams and the topology. But I'm not sure. I mean, it's a computation you have to do, and I'm not sure if it's satisfying for you.
Okay, we might wrap up the discussion there. Thank you very much, and
Thank
please
you.
join me in thanking Thomas for a brilliant talk.